Today we will discuss the radiation resistance. Due to a current element. So, if I have a dipole and if current is flowing through this, and if the length of this dipole is dl and if current I flows through it, then I can call this dipole as a current element. And we had seen that P dot, the rate of change of dipole moment, was coming in terms of P dot was actually equal to I dl, is not it. So, it means a dipole is actually a current element, it can carry current. So, it is a current element, and if this current is changing with time, it will give rise to some radiation, Now, what is the resistance? Radiation resistance. Now, what is radiation resistance? See, in order to feed some current to this antenna or this dipole, because it is a radiating element, so I call it an antenna. Anything that can radiate electromagnetic power is called an antenna. Okay. So, now in order to feed some current to this antenna, I need to give some input power. Okay. Now, that input power is converted into heat, and that heat is radiated in the form of EM waves. Okay. This is a wire, this current carrying element is a wire, and you are giving some current I, some changing time varying current I. Now, this time varying current, now there will be a loss, power loss, that is I squared, that will be R into I square RMS, root mean square value of the input current, because it is a time varying current. So, I will take the root mean square value. Okay. So, it means this is equal to the power loss. Okay. Now, this R will decide that how much heat will be generated, because you are giving a constantly varying current. You know what is the positive amplitude and you know what is the negative amplitude, and it is not going to change. So, you know the pattern of the variation of the input current, but now the power lost or power radiated will depend upon the resistance of the element. Okay. Now, this power loss is converted into heat. This power loss is converted into heat, and this heat is radiated in terms of radiated as EM wave. Okay. So, heat when heat is radiated, it is an EM wave depending upon what is the time variation, how frequently I is varying. Depending on that, the output radiation would be EM radiations. So, now this R is called radiation resistance. This R here is called the radiation resistance. Now, I know that this is I and this is R, but generally when we deal with electromagnetic problem, we deal with electric field and magnetic fields. So, now in the last turn we had considered an oscillating dipole, and we had calculated phi NA. And we had seen that phi component was always 0 for this was scalar potential. Yeah, it is scalar potential, this is vector potential. So, we had calculated this. Now, from here I can write that electric field is equal to minus gradient of A minus del phi by del T. Okay. And I can write that magnetic field B is equal to curl of A, and we had already calculated the values of A and phi in polar coordinates in terms of r theta and phi. Okay. So, using those values which we had calculated for E, for A and phi, now we will try to find out the radial component of electric field and magnetic field. See, phi component was 0, there was no radiation along the phi direction. Okay. So, we had seen that the radiation was along the phi theta direction. Okay. So, now if I calculate what is the radial power E r here, what is the electric field intensity here, and if I can calculate the corresponding magnetic field, then I can calculate that what is the total power that is being radiated from Poynting vector. Okay. If I can calculate E and I can calculate B, then I can calculate the power that is being radiated from this antenna, from this current element due to a small current I. And that how you will calculate power? Using Poynting vector. Poynting vector is E cross H. Okay. It is the cross product of electric field and H. So, now our aim is to first calculate E and B and then calculate the Poynting vector and then equate it to this equation, Okay. So, we will do that. So, I know that P is equal to Q dl. So, I can write that P dot is equal to I dl, okay, and I can write that P double dot is equal to di by dt into dl, okay, di by dt into dl. Is it okay? Now, if I assume that I t is of the form I0 e to the power minus I omega t, let me say this is capital I, because otherwise we will get confused with the small iota there. So, if I t is of the form I naught e to the power minus I omega t, then in that case I can write that this is di by dt is equal to minus I omega I dl. Is it okay? Or I can expand this, or I can write that this is equal to I0 e to the power minus I omega t dl. Now, if you look at the results that we had derived in the last lecture, we derived that ER, radial component of electric field, is equal to four pi epsilon 0 c square P dot by r into sin theta n theta. This is the radial component of E. And also from Biot and Savart law, I can calculate magnetic field intensity at a point P due to this, at some point P due to this current element from Biot and Savart law. Okay. So, that comes out to be Br is equal to 1 upon 4 pi epsilon 0 c square R c P double dot sin theta n phi. Now, epsilon 0 c square is equal to mu naught, epsilon 0 c square is equal to mu naught. So, I can write that this is equal to mu naught upon 4 pi R c P double dot sin theta n phi. So, this is the radial component, radial component of electric, the radial component of electric field, and this is the radial component of magnetic field. Now, here I am telling that the double derivative of the dipole moment P is given by minus I omega I0 e to the power minus I omega t. but we know that we are here doing some gauge transformation, because the E value of E has been calculated as minus gradient of A minus del phi by del t, and that is Lorentz gauge. Okay. So, in gauge transformation we are interested in the retarded potential at some earlier time. So, I will replace this T by T minus R by C. I am interested in some time earlier, because if my dipole is here, okay, and I am interested at some intensity at point P which is at a distance r, okay. So, it means the wave which has reached at point time t here would have started at time t minus r by c from this current element. So, I am interested in the radiation pattern of this current carrying element. Thus, I am interested in some retarded time t minus r c. So, I will write down that retarded time t minus r c p double dot will be equal to minus I omega I 0 e to the power minus I omega t minus r by c into dl. This is here p double dot, this is also p double dot. Now, I substitute the value of p double dot from there into E and B. I substitute the value of p double dot into these two equations from there. So, when I do that, I get E r is equal to minus I omega I naught dl sin theta divided by 4 pi epsilon 0 c square r e to the power minus I omega t minus r by c dl n theta. And similarly, I can do for Br. When I substitute here for Br, I will get minus I omega I naught mu naught divided by 4 pi r c sin theta dl e to the power minus I omega t minus r by c t minus r by c into n phi. Now, what I do? I substitute again mu 0 is equal to 1 by epsilon 0 c square. I say that mu naught is again equal to 1 by epsilon 0 c square. So, I have here epsilon 0 c square into, I can write 1 by c outside. Okay. So, you can see that this and this expressions are same, this and this expressions are same, okay. Only there is a factor of 1 by c. So, I can write that Br, radial component of magnetic field, is equal to modulus of Er divided by c into n phi. Okay. This is what we had derived earlier also, that magnitude of the magnetic field is 1 by c times the magnitude of electric field. So, this is what we had derived. Okay. Now, I know from Poynting theorem I am interested in calculating the power that is being radiated from this current element. Now, see, I was initially calculating the electric field and magnetic field at point P. See, all are in terms of r. Initially when I started, see, I cannot calculate at the dipole because it will become 1 by r. So, distance of the point where I am interested, if it is on the dipole, it is 0. So, everything goes to infinity. So, that was not a correct way of doing. So, what I did, I chose a point P which was a distance r from the radiating element, and then I transformed my time from t to t minus r by c. So, it means now I am actually calculating the wave or the power that is being radiated from the current element. So, now whatever I am going to calculate the power, that is from the antenna element. Okay. So, now I calculate P from Poynting vector, Poynting theorem. The power radiated or power that is being carried by this electric and magnetic field is equal to, or I will say average power is equal to E cross H by 2. This is the Poynting theorem, or I can write that this is equal to E cross H, sorry, I have calculated B, so divided by 2 mu naught. Okay, from the relation between B and H. So, now you can see that E and B have same magnitude. E and B have same magnitude, isn't it? E and B have same magnitude. I mean, it is B is ER by C. Okay. So, I can write here that P average is equal to mod of ER square by C n theta cross n phi. इतना ही difference है. Now, n theta cross n phi is equal to nr. So, power is radiated along the radial direction. Power is, हाँ बताइए, हाँ sorry, that is there 2 mu naught C, that is there 2 mu naught C. So, power is radiated along the radial direction. ठीक है. अब हम इसको रख देते हैं इन वैल्यूज़ को. सो आई हैव P एवरेज, आप ये वैल्यू जो है इसको रख दीजिए तो आपके पास आ जाएगा ओमेगा स्क्वायर I 0 स्क्वायर साइन स्क्वायर थीटा dl स्क्वायर डिवाइडेड बाय 4 pi epsilon naught C square R whole square into 2 mu naught C into NR. Okay. So, I can say this is modulus of P. Okay. See, now this average power is radiated. Now, we are considering the power radiated along the P direction, but the antenna is going to radiate power in all the direction. A current element is going to radiate power in all the direction. So, I need to calculate, so this is in this direction, in a particular direction where I have chosen my point P, but now I need to calculate the total power radiated from the entire surface of this current carrying antenna. Okay. So, it means the total power radiated PT will be equal to total power radiated PT is integral P dot ds, where ds is the elemental surface area of this current carrying element. Now, this current carrying element could be a cylindrical wire, a wire with cylindrical cross section. Okay. So, I can write that this is equal to, in polar system, the area vector can be written as P dot or P r square sin theta d theta d phi. So, it will go from phi 0 to 2 pi and theta 0 to pi, that is ds in polar system. So, now you will see here that all other terms are constant, I will have only sine square theta. So, I will actually integrate sine cube theta for d theta d phi, all other things will be constant. I can take them out of integral. So, I will be left with only sin square theta. So, I will be left with sin cube theta. So, what you need to calculate is the integral phi 0 to 2 pi and theta 0 to pi sin cube theta d phi. इसकी वैल्यू बताइए, बताइए 8 पाई बाई 3 आनी चाहिए. You can use sin 3 theta's formula and you must get 8 pi by 3. Okay? आप इसको चेक कर लीजिए. So, what I get is P total is equal to omega 0 square I 0 square dl square divided by 32 pi square epsilon 0 c cube, where I have converted mu into epsilon 0 c square, okay, epsilon 0 c cube and into 8 pi by 3. Now, what is this? This is the peak value of the current. What is I0? Is the maximum amplitude, okay. So, I can write that I0 is equal to, because it is a time varying current, so I can write that I0 is equal to I RMS by root 2. ठीक है? Is it okay? I RMS by root 2, and I can also substitute that omega is equal to 2 pi c by lambda. ठीक है? And I can say that c square is equal to 1 upon mu naught epsilon naught. So, all known things we will substitute, we will do some modification so that it gets simplified, this equation. So, when I do that, I get P total, this equation gets converted into 2 pi mu naught c divided by 3 into dl by lambda whole square and into I RMS square. Now, mu naught is 4 pi into 10 to the power minus 7 Henry per meter. So, I substitute that. So, I get 8 pi. So, when I so this is mu naught is 4 pi into 10 to the power minus 7 Henry per meters. C is 3 into 10 to the power 8 meters per second. I substitute those values here, okay, and when I do that, then I get Pt is equal to, from here I get Pt is equal to 80 pi square dl by lambda whole square into I RMS square, okay. आप इसे कैलकुलेट करके देख लीजिएगा. I have done this calculation, it comes like this only. Okay. So, in the beginning today I had told you that the total power radiated by any current carrying element is actually the total input power which is being converted into heat, So, I can say that this is equal to R into I RMS square. This is the total power lost. So, whatever the power lost is equal to heat generated in an electrical equipment. So, I can say if I compare these two equations, then I can say that the radiation resistance of this current carrying element, RR is equal to 80 pi square and dl by lambda whole square, okay. This is the radiation resistance of an antenna which is dl length long which is dl length long and is carrying a current I. Okay. So, if the current the behavior of I does not change, if the time variation of I does not change, then I can say that the total power consumed in the form of heat by a current carrying wire is equal to the total power radiated by that current carrying wire. Okay. So, from there what we get is the radiation resistance. Okay. So, the concept now this radiation resistance unit is ohms, because we are equating it to I squared R. So, R is in ohms. So, radiation resistance has also got unit ohms. Okay. So, this concept of radiation resistance is slightly tricky, because a radiating element we are not able to associate resistance with a radiating element. Okay. So, now there are certain few more things like directivity of an antenna. What is directivity? There are few definitions. So, if I say that my radiation pattern from an antenna is something like this. So, this is the front lobe and this is the biggest lobe because it has got maximum amplitude, and this is the back lobe. Okay. So, it is the maximum power radiated by an antenna in a particular direction. It is the maximum power or the direction in which the antenna radiates maximum power. Okay. And it is calculated, it is calculated by the power radiated in a particular direction. So, directivity is the power radiated in a given direction divided by the total average power. Now, what is total average power? See, if this was a point element, if this was a point, okay, and it was radiating in all the direction, if it was radiating in all the direction, then the input power, if it is a current carrying element, if I take any point here, it will be a point. If I say I take this point, so from here power is going in all the direction. Okay. So, what I will do, the average power is the input power given to the antenna divided by the total solid angle 4 pi. Okay. So, it is like this. So, I need to calculate the total, I have to divide to get the average power. You take the input power in watts divided by the total solid angle 4 pi. So, that is the average power. Now, this is very important because this gives us a measure that in which direction an antenna can radiate maximum. So, if you want to radiate or if you want to send some information, then the direction of directivity should be towards the receiver to get maximum gain, okay, maximum efficiency. So, this is about dipole antennas. Now, we have only one article left, and that is on loop antennas, and then probably it will be over.